I am AKB Anjan Kumar Bhuiya from the Department of Mathematics, Vishwabharati. Today we will start chapter 6, which is on the maximal and prime ideals of a ring. Maximal and prime ideals are two special kinds of ideals. Why we are going to discuss such two special kinds of ideals? For this, let me recall the example of the non-commutative group of all 2 by 2 non-singular real matrices. This non-commutative group is denoted by GL2R. If we make quotient by SL2R, then the quotient GL2R by SL2R becomes isomorphic to the multiplicative group of all non-zero real numbers, which is commutative. Similarly, in case of commutative rings with 1, we see that some quotients becomes fields or integral domains. And you know, every quotient ring associates uniquely to an ideal of the ring. So, our question is that which are those ideals M such that R by M becomes a field. So, what is the speciality of such ideals? For this, let us recall the following important characterization of fields using ideals. The result states that a commutative ring R with 1 is a field if and only if it has only two ideals, namely 0 and R itself. This result, together with the correspondence theorem, give us an idea about such ideals. Let R be a commutative ring with 1 and J be a proper ideal of R. Then R by J is a commutative ring with unity 1 plus J, and the correspondence theorem tells us the ideals of R by J are of the form I by J, where I is an ideal of R which contains J. So, R by J will have no ideal other than 0 plus J and R by J if and only if J is not properly contained in any other proper ideal of R, from which we formulate the following definition of the maximal ideals. Suppose R is a commutative ring with 1, then an ideal M is said to be a maximal ideal of R if M is proper and M is not properly contained in any other proper ideal I of R. This actually says that M is a maximal element in the partially ordered set of all proper ideals of R. Before going to further characterizations of the maximal ideals, let us discuss this example where we will find some maximal ideals in the ring Zn of all integers modulo m. Consider Zn where n is greater than equal to 2. We show that for every prime divisor P of n, the ideal generated by box P is a maximal ideal. To prove the maximality, consider an ideal I of Zn such that the ideal generated by box P is properly contained in I. If we can show that I is nothing but whole Zn, then it will be proved that the ideal generated by box P is a maximal ideal. Since I properly contains the ideal generated by box P, we must have some box A which is in I but not in the ideal generated by box P, and so it follows that P does not divide A, and hence GCD of AP must be 1. Then the Bezout's identity gives us 1 equal to AU plus PV for some integers u and v, and which implies that box 1 is equal to box A into box u plus box P into box V. Since box A is in I and I contains ideal generated by box P, so box P is also in I, and hence box A into box u plus box P into box V belongs to I, which implies that box 1 is in I. Since box 1 is the unity of Zn, it follows that I must be equal to Zn, and thus it follows that ideal generated by box P is a maximal ideal, from which in particular we can say that the ideal generated by box 5 is a maximal ideal of Z25, and in case of Z36 ideal generated by 2 and ideal generated by 3 are two maximal ideals. Now we show that really quotient by a maximal ideal is a field. Formally, if R is a commutative ring with 1 and M is an ideal of R, then we have M is maximal if and only if R by M is a field, that is the quotient of R by M is a field. This is a necessary and sufficient result. First, to prove the necessary part, assume that M is a maximal ideal of R. Since R is assumed to be commutative ring with 1, the quotient ring R by M is also a commutative ring with unity 1 plus M. And since we have assumed M a proper ideal, so the unity 1 plus M must be distinct to 0 plus M, the 0 element of R by M. So we have seen that the quotient ring R by M becomes a commutative ring with unity 1 plus M. Hence, to prove R by M is a field, it remains to show that every non-zero element of R by M has a multiplicative inverse. Consider a non-zero element A plus M. Since this is non-zero, so A cannot belong to M, and since M is maximal, so the ideal generated by M A will be equal to R. This actually follows from the maximality of M. Again, 1 is in R and hence is in the ideal generated by M A. So we have some M in M and R in R such that 1 equal to M plus R A, which is equivalent to 1 minus R A belongs to M. Thus, R plus M into A plus M becomes equal to 1 plus M, which shows that the non-zero element A plus M has an multiplicative inverse R plus M in R by M. Thus, it follows that R by M is a field. Now, for the converse part, assume that M is an ideal which is such that R by M is a field. Since in a field the unity is distinct from the 0 element, so here we have 1 plus M is distinct from 0 plus M, and so R cannot be equal to M. That is, M becomes a proper ideal of R. Now to prove the maximality, assume that there is an ideal of R which properly contains M. We show that R must be equal to R. For this, consider an element A from I which is not in M. Since A does not belong to M, so A plus M is non-zero, and so there exists R plus M in R by M such that R plus M into A plus M equal to 1 plus M, which follows from the fact that R by M is a field, and this implies that 1 minus R A belongs to M. Now, M is a subset of I, and hence 1 minus R A belongs to I. Again, since A is in I, so R A is in I, and it follows that 1 belongs to I, and since I contains the unity 1, so it follows that I must be equal to R, and thus it follows that M is maximal. Now, we will apply this result to characterize all maximal ideals of the ring Z of all integers. You know that every ideal of Z is of the form Nz, where n is an integer. Consider an ideal Nz. Then Nz is maximal if and only if the quotient ring Z by Nz is a field, and we know that this is if and only if n is a prime. Thus, the maximal ideals of the ring Z are of the form Pz, where P is a prime, and conversely. So, for example, 2Z, 3Z, 5Z, 7Z, etc. all are maximal ideals, but 4Z, 6Z, 8Z, these are not maximal ideals. Now, before to proceed further with maximal ideals, we should answer whether there is a maximal ideal M of each commutative ring with 1. Actually, the answer is positive, that is, given any commutative ring R with 1, there is a maximal ideal. We will prove this using Jones' lemma. This is a result which is equivalent to the set theoretic axiom of choice. Here we will not discuss anything on the axiom of choice. Actually, we are concerned with its abstract algebraic equivalence, Jones' lemma. Jones' lemma is on a partially ordered set. Now, we recall maximal elements of a partially ordered set and chain. Suppose P is a partially ordered set. An element U in P is said to be maximal if there is no element x in P which is strictly greater than U. That is, U may not be greatest among all others, but U is not smaller than any other element. Such elements are called maximal. This is unusual to us because we are familiar with only fully ordered sets which we see in R or in N. But since this is a partially ordered set, it may be that there are two elements which are not comparable. That is why such a situation arises that there is an element u about which we cannot say that u is the greatest among all other elements, but it is also true that u is not smaller than any other elements. And a chain is a partially ordered set such that any two elements A, B in C are comparable. Jones' lemma states that suppose P is a partially ordered set if every chain in P has an upper bound in P, then P has a maximal element. We will apply Jones' lemma on a partially suitably chosen partially ordered set of ideals and find out its maximal element, and finally we prove that that maximal element will be a maximal element which we are trying to find out. So, formally speaking, if R is a commutative ring with 1 and I is a proper ideal of R, then we have a maximal ideal that contains I. This is more than mere existence of a maximal ideal. Actually, it states that every proper ideal is contained in a maximal ideal of R. Since we want to use Jones' lemma, first we have to construct a partially ordered set. Denote a set A to be the collection of all proper ideals J of R which contains I. Since the ideal I belongs to this set A, so A becomes non-empty. Also, A is a partially ordered set with respect to the usual set inclusion relation. Now, we show that every chain in A has an upper bound in A. For this, consider a chain C which is indexed by lambda. Since this is a chain, that is, any two ideal J alpha, J beta in C are comparable. So, their union J alpha, where alpha runs over lambda, is an ideal of R, and also this is a proper ideal of R. Otherwise, if this union becomes equal to R, then 1 belongs to this union and hence belongs to some J alpha which is again in A, but A is a collection of proper ideals. So, the union J alpha is a proper ideal, and also it is trivial to note that the ideal I is a subset of this ideal, and hence this is in A and is an upper bound of C. Thus, we see that A is a partially ordered set in which every chain C has an upper bound in A. So, by Jones' lemma, A has a maximal element, say M. We claim that this maximal element M, we show that is a maximal ideal of R. Suppose K is an ideal of R which is proper and contains M. Since I is a subset of M, so I is a subset of K and so K belongs to A. Hence, from the maximality of M in A implies that M equal to K, and hence it follows that M is a maximal ideal of R. Thus, we see that if I is a proper ideal of the ring R, then there is a maximal ideal M which contains I. Now, as an application of this result, we will have two results. First, every non-unit element is contained in a maximal ideal, and the second is that if R is a non-trivial commutative ring with 1, then it has a maximal ideal. First, assume that A is a non-unit element of R, then the ideal I generated by A is a proper ideal of R, and hence it is contained in a maximal ideal M which follows from the previous result. And next, suppose R is a commutative ring with 1 which is non-trivial, that is 1 is not equal to 0, then it has a maximal ideal. Here we consider 0 to be a proper ideal of R. Actually, to make 0 a proper ideal, we have to consider 1 is not equal to 0, equivalently R is non-trivial. Since 0 is a proper ideal of R and hence 0 is contained in a maximal ideal, say M. Thus, finally, we have the result that if R is a commutative non-trivial ring with 1, then it has a maximal ideal. We know that the set of all units of a ring R, if we denote it by UR, is a multiplicative group. Consider the set of all non-units of a ring R. Now, the question is that does it have an algebraic structure? That is, can we say that the set of all non-units of a ring is a subring or anything like this? This question is closely related to the idea of maximal ideals. Now, we show that this is a subring if and only if the ring R has unique maximal ideals, and such rings which has unique maximal ideal are known as local rings. Now, we characterize those commutative rings with 1 which have unique maximal ideal. This question is closely related to the set of all non-units of R. Recall that the set of all units UR is a multiplicative group, and let us denote the set of all non-units by MR. Now, the question is that is MR a subring of R? We see that this is a subring if and only if R has unique maximal ideal, and we call such rings local rings. Local rings are very fundamental in the theory of commutative rings, but here we do not have the scope to go into the details. Here I give only definition and simple equivalent characterization of local rings. We define a commutative ring R with 1 to be local if it has unique maximal ideal. Now we show that a commutative ring R is local if and only if the set MR of all non-units in R is an ideal. The idea comes from the fact that no proper ideal contains a unit. Thus, if MR equal to R minus UR, that is if MR is the set of all non-units, then every proper ideal of I is a subset of MR, and hence if MR is an ideal, then this becomes the unique maximal ideal of R. To prove formally, suppose first that MR is an ideal, and if I is a proper ideal of R, then I is subset of MR, and thus MR becomes unique maximal ideal of R. Conversely, suppose that R is a local ring and M is the unique maximal ideal in R. Since M is proper, so every element of M is a non-unit, hence M is a subset of MR. Consider an element A from MR, then A is contained in a maximal ideal. Since A is non-unit, it follows. Thus, MR becomes a subset of M, and it follows that MR equal to M. Therefore, MR becomes an ideal of R. Now, I give two examples of local rings. First, I characterize N for which Zn is local. Let n greater than equal to 2 be a positive integer. We show that Zn is local if and only if n is a power of some prime number p. Recall that in the ring Zn, we have for every prime divisor of n a maximal ideal generated by box P. We will use this result here. First, if we assume n equal to p to the power r, then box A belongs to Zn is a non-unit if and only if GCD of a p to the power r is not equal to 1, and that is p divides A. It follows from the fact that p is prime. Thus, the set of all non-units is the ideal generated by box P. Hence, Zn is a local ring. For the converse part, since every prime divisor P of n gives us a maximal ideal, hence if Zn is local, then n cannot have more than one prime divisor, and hence n must be of the form a power of some prime number. Thus, it follows that Zn is a local ring if and only if n is a power of prime. Our next example is the ring of all periodic integers. Let p be a prime number, then the collection of all rationals a by b such that p does not divide b is a ring which we call ring of periodic integers. We show that this is a local ring. For this, note that an element A by B of this ring is a unit if and only if we have B by A is also in this ring, for which we need A is not divisible by P. Thus, the set of all non-units is the collection of all A by B such that A is divisible by P. It is easy to check that M is an ideal, and hence it follows that QP, the ring of all periodic integers, is a local ring. Thus, we have characterized in this module the ideals whose quotient is a field, and also we ensure that every commutative ring with 1 possesses such an ideal, and characterized the local rings, that is the rings which has unique maximal ideal. In the next module, we will characterize the ideals P such that R by P is an integral domain.